We have seen in the previous class that when a particle is confined inside a box, its energy becomes quantized. We have also seen that the magnitude of the particle energy depends the size of the box in which it is confined. Today, we use the same example to demonstrate the quantum confinement effects in semiconductors. Normally, in physics, when we speak about motion of something, it occurs in three dimensions. Even in a narrow box, in classical physics, a point particle of zero size would be able to move in all three directions. But in quantum mechanics, if the box gets very narrow, the motion becomes truly one dimensional. To understand why, we have to first understand what actually motion means. You know that classical physics define motion as the change in position of an object. This definition creates some issues in quantum mechanics because we now know that the particles do not have a well-defined position in quantum mechanics. So, without a well-defined position, defining motion is something a tricky process. So this definition is not valid in the case of quantum mechanics. So let's assume that the particle is in the ground state of lowest energy, that is the 111 state, where all three quantum numbers are in its lowest possible value. It tells you that the ground state has a non-zero energy and it is all kinetic energy. But we saw that the probability of finding the particle was not changing with time. All the other energy eigenstate also have the same boring property of not changing with time. So it sounds weird, right? If the particle has kinetic energy, then why not the position of the particle change with the time? The answer is that in quantum mechanics, the kinetic energy is not directly related to the changes in the likely positions of a particle. The old definition of kinetic energy related to the motion of particle is only an approximation valid for macroscopic systems. It is not necessarily true for quantum scale systems, particularly if they are in the ground state. In quantum mechanics, the kinetic energy is defined as the second order derivative of the wave function and nothing else. Now something interesting will happen if we combine states of different energy. For example, let's consider the possibility that the particle has the wave function given by this expression. Psi is equal to square root of 4 by 5 psi 11 plus square root of 1 by 5 psi 211 at time t equal to 0. This is what we mean by saying that the system is in a superposed quantum state. Here we have considered the superposition of just two states, psi 111 and psi 211. In principle, the system can be in a superposed state of all possible eigenstates of the system. According to orthodox interpretation, this means that in an energy measurement, this particle would be 4 by 5, that is 80% of chance being found at the ground state energy E111 and 20% chance of being found at the elevated energy level E211 at time t equal to 0. So now there is an uncertainty in the energy, and that is very critical. To know the state of the system at a later time, we have to consider the connection between the time independent wave function and the time dependent wave function, which is given by this expression, and this we had seen in the previous class. So we can say that the wave function at a later time will be like this expression, where we have added the time dependent part to this wave function that we have considered. Then the probability of finding the particle, that is the square of this psi, can be plotted for various time. If you take a snapshot of probability at various time, you will get the probability density like this plot. Each of this plot is the probability density corresponding to this particular state at different times. So this may be for some time t1, this is for another time t2, t3, t4, etc. Or if you record it like a movie, you can see that this probability of likely positions of the particle actually changes with time. It oscillates between the ends of the boxes. Thus, with the uncertainty in energy, the wave function blob does move. It performs a periodic oscillation. Even though the particle is not localized, at least the locations where the particle can be found are now bouncing back and forward between the ends of the pipe. And if you add additional wave functions like psi 311, psi 411, etc., you can get closer and closer to a localized wave function blob bouncing around. If you have a closer look on the figure, you will note that the wave function blob does not move at all in the y direction. There is no movement in the y direction. The only movement is along the x direction. It remains at all times centered around the horizontal direction. In principle, this is not a big deal. What we have to do is just add one or more wave functions with any ny value, that is the quantum number along the y direction, greater than 1. For example, if you add the states to this function, the states like psi 121, psi 131, etc., then what we expect is a movement along the y direction can also be possible. But there is a catch, and it has to do with the required energy. Let's consider the expression for energy along y direction shown here. So the kinetic energy in the y direction takes the values like this one. The minimum energy along the y direction is given by h cross square pi square by 2m ly square. This ly is the length of the box along the y direction. The next possible energy value along y direction is 4 times of this one. The next possible is 9 times of this value. In the example of a particle in a box, we considered a box in which the length along the y direction is much smaller than its length along the x direction. That means Ly is much shorter than Lx, and hence the lowest possible energy along y direction will be much larger than the lowest possible energy along x direction. Even though this y direction energy is higher, the particle will certainly have this energy if it is in the box. But if the box is really narrow, it will simply not have enough additional energy to get anywhere close to the next energy level, let's say Ey2 or Ey3, etc. That means it is very unlikely for the particle to be found in states with energy Ey2 or Ey3 or any higher energy states. Hence, we are unable to consider superposition of y direction wave functions, because the only possibility for the particle can have along y direction is this lowest energy and it corresponds to only one quantum state. Since these are not achievable, you cannot add or you cannot consider a y direction wave function in a superposed state. So without considering a superposed state, there is no possibility of getting moving wave function. The kinetic energy in the y direction will therefore be stuck at the lowest possible level, EY1, or in other words, there is absolutely nothing interesting goes on in the y direction. As far as a particle in a narrow box is concerned, it looks like the y direction does not exist at all. It is ironic that while the kinetic energy in the y direction is very large, there is no change in the probability density with respect to time, and hence it appears like there is no movements in y direction. Now, in the example of particle in a box, the length of the box along the z direction was considered still smaller than the length along y direction, and hence the kinetic energy in the z direction is still larger than that along the y direction, and hence we do not expect any motion along the z direction also. So we can conclude that if the box is very narrow in the y and z directions, the only interesting motion will be along the x direction, and hence we say that the motion is one dimensional. So this is the case of quantum wires, where we physically restrict the cross-sectional dimensions much smaller than the length of the material. In such cases, electrons will be moving along the length of the wire without any kind of motion in other two dimensions. So this is totally different from classical understanding. According to classical physics, a point particle should be capable of having three-dimensional motion, however small will be the dimension of the box. Quantum mechanics tells you that this three-dimensional motion is not true. If you restrict the size of the system, its motion will be truly one-dimensional. Now let's consider a situation that the size of the box in the z direction is relatively wide, like this one. You have a lengthy box along x direction, and there is sufficient length along z direction, but the length along y direction is very small, like what we considered for previous example. Then, in addition to the availability of many energy states along x direction, the particle will have lots of different energy states in z direction available too, and hence it is possible to the motion along that direction, and hence it is possible to have motion along the z direction as well. So what happens in such cases are that in addition to the movements along this x direction, the particle can now move along the z direction as well. So altogether the particle can move in two dimensions or in a plane, in the xz plane for this particular case. So this is the situation in a quantum well structure, where electrons are free to move in a plane where it has restricted motion along the third direction. Physically, a quantum well structure is fabricated by sandwiching a low band gap material in between a high band gap material like this one. If the box is narrow in all three directions, you get a zero-dimensional quantum dot in which the particle does nothing unless it gets a huge amount of energy. So there is no free movements of electrons in such quantum dot structures. An isolated atom can be regarded as an example of a quantum dot, as the electrons are confined to a small region around the nucleus and will be at single energy level unless they are given a considerable amount of energy. But note that when people talk about quantum confinement, they are normally talking about semiconductors for which similar kinds of effects occur at a significantly larger scales, maybe tens of times as large, making them much easier to manufacture. An actual quantum dot is often referred to as an artificial atom and has similar properties as a real atom. We have seen that the energy levels of a particle trapped inside a box can have only quantized values given by this expression for a one-dimensional box. If we consider the energy difference between any two successive quantum states n plus 1 and n, we can see that it is inversely proportional to the square of the size of the box in that direction. That means if you have two one-dimensional boxes like these, the energy levels in shorter box will be having more separation than the other one. This is an interesting point as it enables us to manipulate the electron energy levels in a material by simply playing with the size of the material. This is the underlying principle in nanotechnology, where we restrict the motion of electrons in various directions by changing the dimensionality of the normal three-dimensional objects into a lower dimensional one and thereby modifying the energy spectrum of the object. So this is quite exciting to know that we have arrived at the foundations of nanotechnology by solving a simple quantum mechanical problem.